As you know, because we just got this subject started last time, I'm going to talk today about ice in the climate system. Let me just review the types of ice that we'll be speaking about. Sea ice, which is frozen seawater. Ice sheets, which there's only two of those existing today in the modern world, and that's Greenland and Antarctica. We'll talk about those. Later on next week, when we talk about climate change, I'll describe to you how in earlier days there were some other ice sheets on Earth, but at the moment there's just those two. We'll talk about how they work. Glaciers, both coming down from ice sheets and from mountain glaciers, ice shelves, icebergs, and permanent and seasonal snowfields. So we'll be going through those subjects today. And I mentioned these items last time as well. There are certain important physical properties that you'll need to understand in order to understand really how ice behaves on our planet. And I won't go through those again today. I went through them at the beginning, at the end of the period last time. But just review those. We'll be discussing those as we go. So let's start with sea ice. And what I've shown you here are some diagrams that illustrate how sea ice changes with season in the two hemispheres. Now remember, this is frozen seawater. So in the about this time of year, late October, you begin to get cold air blowing over the sea surface in the high northern latitudes. So we'll focus on these two diagrams. And as the cold air blows over the ocean surface, it draws heat out of the ocean, cools it down. When you get the temperature down to about, not zero, but about -2 Celsius, because the salt depresses the freezing point by that much, then you start to get sea ice forming. It starts usually in small little patches of ice called pancake ice. I'll show you that in a minute. And then as the season progresses, you freeze the water in between, and those little pieces of ice stick together, and a month or two later, you've got a more or less continuous layer of sea ice in these high latitude regions. And then during the winter, it deepens. In other words, you're drawing heat out of the bottom and you're freezing more ocean water onto the bottom, and so the thickness of the sea ice increases. So here we are in September, which is at the end of the warming season. That would be the minimum in the sea ice, and yet there is some sea ice remaining from the previous year. Then we begin to build new sea ice, and about 6 months later, this is typically, or at least was, we'll talk about the fact that it's changing with time, but this is typically how far sea ice extends at the end of the cooling season. Then it begins to warm again, and over the summer you melt away a lot of this and you end up back towards the minimum. So there's a big seasonality in sea ice, and this is the way we understand it. In March, when you've got maximum sea ice, you have a stream of sea ice coming down on the east side of Greenland. Most of Baffin Bay is filled with sea ice. All of Hudson's Bay and James Bay is filled with sea ice, and really it even comes out a bit into the North Pacific. But this area stays generally free of sea ice, and you know why that is, because you remember that the part of the Gulf Stream splits off and moves up into that region. So even at the maximum of sea ice, you still have open water along the coast of Norway, and even up here in an area that's called North Cape. Now, of course, in the southern hemisphere, the seasons are reversed, and so it's in March that you'll have the minimum of sea ice, because that's when you're at the end of the warming season, and it's pretty much drops to zero. In other words, you have a little bit of permanent sea ice remaining, but really very little. And then 6 months later, at the end of the cooling season, you've grown quite a remarkable area of sea ice by, again, freezing seawater. Later on, I'm going to be showing you what the ice on Antarctica is doing, and we'll talk about ice shelves, but keep that distinct from what we're seeing here. This is the frozen seawater, the sea ice that I'm referring to. Any questions on that? Yeah.
Is it because the Gulf Stream waters are warmer, or they're just moving faster?
They're warmer. So even in wintertime, the temperature of the sea surface here is about +3 or +4 Celsius. And remember, the freezing point is -2, so you're not going to get freezing of these waters, even though you get terrific cold winds coming off of that sea ice. I was on an expedition up there 20 years ago, right at the edge of this sea ice, looking at how that cold wind was coming off and trying to freeze the water, but there was so much heat convecting out of the water that you weren't able to cause any new sea ice forming in that area. So it's the warmth of that Gulf Stream extension that's keeping that free of ice. Yeah?
How deep is the ice?
I'll talk about that, but typically it's from at the end of the freezing season, you can freeze ice about 1 meter deep. But if you mechanically stack it up, which happens in some parts, you can get it to be about the height of this room, 3 or 4 meters high. So compared to the ocean depth, it's tiny, just the thinnest skin. But in terms of real physical dimensions, I would say maybe 1 meter at the end of the cooling season in some cases, up to 4 where the ice has been mechanically crushed and stacked. Now, I want you to notice something. In the Arctic Ocean, it's ocean at the North Pole, and it's confined by continents around. And you typically fill that up, and you can't go any further, of course, because you can't make any sea ice over the land. So if you're going to monitor this sea ice year by year, the way it's typically done in the Northern Hemisphere is to monitor the minimum sea ice, which is in September. Maximum wouldn't make much sense because you're not going to fill that in with ice, and you've already taken it shore to shore in the Arctic Ocean. So the way you monitor interannual variations or trends is to keep track of the minimum. On the other hand, in the Southern Hemisphere, the minimum is pretty much zero. You have a continent filling the South Pole, and you're not going to form any sea ice there, and the sea ice itself pretty much goes back to that shoreline. So the way we monitor sea ice in the Southern Hemisphere typically is by the maximum sea ice that you grow. Notice then that means September is kind of the month where we monitor sea ice in both hemispheres, even though the seasonality is opposite in the two hemispheres. So be aware of that. It's a curious way that we decide to monitor these things. So pancake ice looks like this. So when the winter's beginning and the cold air is drawing heat out of the ocean, for a period of some days or weeks, you have little chunks of ice that are from, half a meter to a couple meters in diameter. They have rounded edges because with the wave action, they keep bouncing into each other, breaking off any sharp corners. And then a few weeks later, you begin to freeze and get a more continuous ice. This happens to be continuous sea ice with compression ridges. In other words, when you look at these features like this or that, that's an area where the wind has blown the sea ice together and it has crumpled along a line. And so if you're traveling over sea ice, as the early explorers were trying to do, travel over the sea ice to reach the North Pole, it's not like some skating rink where you can just ski or skate across the sea ice. In fact, every few hundred meters, you end up climbing over one of these compression ridges, which makes traveling there extremely difficult. You have to pull your sledges or whatever kind of equipment you have up over these ridges, and then down. You get maybe 50 or 100 yards, and then you're doing it again. So it's very rough going when you're trying to cross the sea ice. Yeah.
How tall do the ridges get?
So the ridges will get typically only 4 or 5 meters high, but remember they've got a root, which you don't see, but in order to support that extra weight, they also have a root that goes down beneath the ice. So if you measured it from top to bottom, it might be 20 or 30 meters, but the part you have to climb over is just 3 or 4 meters, something like that. Yeah.
How are they
by compression. So the wind, for example, blowing over the ice will try to push it, but if it comes up against the shoreline, it can't be pushed any further, and so you'll end up just crumpling that ice and stacking it up along these ridges. Yeah, good questions. So here's another picture of sea ice. And I wanted to ask you, first of all, was this picture taken in winter or summer? Would you guess? Why? Why was that? It was taken in summer. How would you know that? Sorry? Yeah, it's got some meltwater in between here, but there's even a more obvious answer than that.
Do they hibernate in the winter?
That's true also, but there's even a more obvious answer than that.
It's sunlight.
It's sunlit, exactly. So you could not take a picture like that in the wintertime. It would be pitch dark, all right? So it is true there's melt ice. It is true the polar bear is walking around. But even more obvious is it's sunlit, right? So that means in those latitudes, that's got to be a summertime picture. Just a trick question for you this morning, seeing if you're awake. So let's take a look at what happens. This is a short movie, and it'll just show you, remember the date is up here, and you'll watch that change, and so we'll just watch how one season sea ice grows here. So it's growing now, filling out the basin. Look what's happening in Hudson's Bay, filling in James Bay too. Still growing a bit up here, but it's now about as far as it's going to get. A little bit of extra growth there in Baffin Bay, a little bit more growth in the current bringing it down, and then there we are in March. So that's kind of at the maximum. The movie just takes you from minimum to maximum last year in the year 2010. Now what will happen after that, not shown, is that this will all begin to melt back, and we'll end up back towards that minimum September distribution. Let me play that again, just so you can, in case you missed something. Every place you look at, you see a little different story there. Also, the zooming in is distracting a little bit. The shade of white gives you something about the thickness or the continuity of the sea ice. If there's gaps, that'll show up as a slightly darker shade of gray. Okay. So Rachel asked about thickness. Here's some examples. The mean from 1982 to 2003. Now it's difficult to measure ice thickness. There are various ways to do it. The earliest way was to take a submarine. In the late 60s, they finally got nuclear submarines that could pass under the ice sheet. And then with an uplooking sonar, you could measure the bottom and the top of the ice and get a thickness measurement that way. Of course, you can go there in situ, but then how do you want to get some measurement that's kind of representative of a large area. It's hard to do that if you're just walking around on the ice with some kind of way of drilling through. So now there's a way to fly over it and use down scanning atmospheric acoustic waves or electromagnetic waves to measure sea ice thickness as well. So it's not a perfectly solved problem, but this will give you some idea. The scale is down at the bottom. It's in meters, from 0 to 4 meters. And it's over on the north slope of Canada, north slope of Alaska, and then along the Canadian archipelago, where you get this deeper ice. And that, I've made the case for you, is not, you can't grow ice that thick thermodynamically by freezing at the bottom, because after it gets to a certain thickness, you remember you have to take the heat out the top. That's where the atmosphere is cold, and yet you've got to freeze the water at the bottom. And after a while, it becomes too hard to get that heat to conduct out through that layer of sea ice. So you can only grow sea ice thermodynamically to this kind of thickness. This is a mechanical stacking process. And you can understand that if you remember that across the Arctic Ocean, there is a current called the transpolar drift, and also the Beaufort Gyre. But that's going to be carrying ice and pushing it up against the north coast of Greenland and along the Canadian archipelago, and then causing that compression ridge to form, those compression ridges, and that deepens the average ice thickness to as great as 4 meters. In other words, typically a little higher than the ceiling in this room. Questions on that? So here's what's been going on the last couple of decades. So this is the Northern Hemisphere extent anomaly. Remember, we're learning to understand this word anomaly because it's often used in climate analysis. What they do is take a measurement and then subtract off a mean value to just emphasize the changes that have occurred. And this is expressed in percent, and 0 is here. So they've taken a year, they've taken 1979 to the year 2000 as their reference time, subtracted off the mean, and then here's what's left as the residual or as the anomaly. So basically, in the early part of the time, it had a positive anomaly by definition, and as it's decreasing, and then near the end, you get a negative anomaly. So really, the change has been remarkable. Overall, that's about a 40%, if you count this, maybe even a 50% decrease in the area covered by ice in September. That's in the minimum period after the warming season. There was quite a shock, and you read about this in the newspaper perhaps. Back in 2007, we had this remarkable drop in sea ice extent in the Arctic Ocean. Then it rebounded, and people were saying, well, maybe that was just an anomaly. Well, it was an anomaly, but now it's come down again. So the point is, it's been noisy all along, right? But nevertheless, the downward trend is very clear. And what I would expect to happen in the future, it would decline further, but be very noisy from year to year. And you can extrapolate this for yourself. In another 20 or 30 years, it seems like we'll have an ice-free Arctic Ocean at the end of the warming season. Questions on that? So the southern hemisphere, again, September. This is the maximum because the minimum doesn't make any sense. It pulls right back pretty much to the shores of Antarctica. That's pretty flat, or if you looked at it very closely, it's even increasing ever so slightly. And so this trend in sea ice that we see in the northern hemisphere is not found in the southern hemisphere. When we're talking about things like global warming, we'll come back and refer to measurements such as this one. But remember, this has a somewhat different meaning because this is the maximum extent of sea ice, whereas the other one for the northern Arctic Ocean was the minimum extent of sea ice. Any questions on that? And of course, what's also in the news is that now, as in the Arctic Ocean, you get a retreat of that minimum sea ice in September. You've opened up these two long sought navigational routes. For years and years in the 17th and 18th and 19th centuries, sailors were seeking the Northwest Passage, trying to find a way to get between the Atlantic and the Pacific without going all the way under Cape Horn. And this was what they were trying to do. They never achieved it, but now today you can. There was a month or so in the summer when you can take a ship through the Canadian archipelago free of ice and transport back and forth. And in the last, well, at least in 2007 and in this year, there's actually a northern sea route along the north coast of Russia that you could use also to get back and forth between the two oceans. So navigation is now becoming possible in the Arctic Ocean, and so is things like oil drilling. So there's been a lot of discussion about who's going to lead the charge to now developing oil resources in the Arctic Ocean. It's quite a change going on up there. So any questions on sea ice? This was all about frozen seawater. Any questions on that? Yeah, Julia. Yeah, so the cold wind blows over the sea, draws heat out of the ocean, drops the temperature down to 0 degrees Celsius, then below, down to -2 Celsius. And at that point, then you start to freeze. And of course, you have to, I showed you on the first slide, you've got to draw a certain amount of heat out for every kilogram of ice that you make. That's called the latent heat of freezing. And so as you continue to draw heat out, the temperature doesn't drop anymore, but you continue to build deeper and deeper ice. So that continues through the month of March in the northern hemisphere. Yep. So now we turn to ice sheets, which is generally defined as a large plateau of ice. And there's two things you have to know to understand this. First of all, on the high altitude parts of the ice sheet, this happens to be Greenland, but it'd be the same for Antarctica, you have an excess of accumulation every year. So more snow falls during the winter than would melt off, if indeed there's any melt at all in the summertime. And so year after year, you just accumulate. Well, that can't go on forever. I mean, if you accumulated a meter of snow or 10 meters of snow every year, by the time you got to 10 years or 100 years or 1,000 years or 10,000 years, you'd have an enormous pile of snow. So that you have to balance that, and what happens is that under its own weight it begins to sag and to flow. So the snow gets compressed into more or less solid ice, and then that ice itself, under high pressure conditions with a lot of weight above it, will begin to flow out toward the edges of the continent. You can simulate this the next time you've got pancakes for breakfast. Just keep pouring that syrup right in the middle of the pancake, and it only gets so deep. After a while, it begins to flow off the edges. And that's exactly what's happening. It's just gravity forcing that viscous fluid toward the edges of the pancake. Then near the edge, there could be some loss by melting or direct sublimation. Sublimation is when you go directly from ice to vapor. But if that's not sufficient, then the ice will actually be squeezed out and will reach the ocean, and then you'll break off those chunks as icebergs. So, but in any case, you've got to balance the mass by having this flow moving from the center towards the edge, and that's the way ice sheets work. That speed is not very great. It may be only a meter per day or even a meter per week. Those flows can be quite slow, but nevertheless, they balance this annual accumulation of snow on the high parts of the ice sheet. You can imagine then, if you have this spreading going on, there has to be some kind of a divide. Just like when we did the river trip, we understood that there is a divide between watersheds. Rain that falls on one side goes into one river, rain that falls on another side goes into another river. The same is true with ice. It's called an ice divide, so that a snowflake that falls here will end up being squeezed out towards the west coast of Greenland. Snowflake that falls there will be squeezed out towards the east coast and the north and so on. And Antarctica has similar divides. They're drawn here. There's quite a number of them actually, but each snowflake then will be squeezed out ultimately towards one part of the coast or the other, depending where they fall relative to these ice divides. Any questions on that? So when you're up on the Greenland ice sheet, it looks like this. More or less continuous sheets of deep ice. There may be a kilometer or more of ice beneath you, very deep ice. Occasionally you may get a rocky outcrop, a so-called nunatak, where a mountain ridge sticks up through the ice, but for the most part there's very deep ice, maybe a kilometer or two of ice beneath you. And you don't have any sense of that slow creeping motion, at least not here where it's smooth. When the ice squeezes out to the edge, in some places, when it reaches the sea, it'll maintain its continuity as an ice sheet, but spread out and begin to float over the sea. Those are called ice shelves. And I've shown you the dominant ice shelves here for Antarctica. There's the Ross Ice Shelf, the Ronnie, and the Larsen. And here's a zoom of the Antarctic Peninsula showing the Larsen ice sheet there. So while that's floating out over the ocean surface, do not confuse it with sea ice. It is still compacted snow. It's fresh water in compacted snow that's flowing out and floating over the ocean, being squeezed off the continent in that way. So it looks like this. Well, at least the part you can see looks like this, but remember, there's another 90% or so, most of it is beneath the water surface because of buoyancy considerations. But that's an example of an ice shelf, a thick layer of ice. Here's a ship for scale. And basically the ice is attached to the land, but eventually as it flows off, you get water underneath. It floats up. Remember, ice is less dense than water, so it floats on the water and flows on out as an ice shelf, and then eventually it breaks off to form icebergs. Questions there? Now, back in 2002, it was in the news that the Larsen ice shelf, or part of it, had collapsed. So here's a sequence of satellite images, January 2002, February, late February, and then March. So here's the Larsen ice. Remember, that's on the coast of the Antarctic Peninsula. I just showed that to you. It looks like there's already some weakening going on here, but then over the next month or so, most of that broke away and floated on off as icebergs. There's some argument in the scientific literature about the significance of the sudden loss of an ice shelf like this. Some would say, well, it doesn't really mean anything because that ice has already left the continent. It's already floating over the sea, and it'll be replaced. In other words, in the natural flow of things, even in a steady state climate, this ice has to be replaced by new ice coming off the land. Others would say, no, a catastrophic loss like this will actually have an effect back over the land and will accelerate the rate at which glaciers are flowing off the land onto the sea. So that argument's a little bit unresolved, but there probably is some climatic significance when you see a sudden collapse of an ice shelf like that, but it can be argued one way or the other. Questions there? Greenland doesn't have much in the way of ice shelves. There's glaciers being produced all along both coasts, but there's an area up here called the Petermann Glacier that it might be argued has the nature of an ice shelf. There's the Petermann Glacier. It certainly looks like that. It's got a broad, flat appearance. It's floating at this point. I'll show you the geometry of that here. So here we are. We're up in the northwest corner of Greenland. There's some barren land with no ice on it, but here comes a glacial stream coming down from the ice sheet. And at some point it does float out over water, and while it is confined to a fjord, it is floating as a more or less continuous ice sheet. And so I guess even though it's confined, it could be called an ice shelf, and then it will have a point where it breaks off and becomes icebergs at that point. And back just last year, in 2010, this was in the news, that a big chunk, between July and August of last year, a big chunk of the Petermann Glacier broke off, and then this big, flat, huge tabular iceberg drifted northwest into the Strait of Nares and ended up blocking that channel for a number of months. Okay, we're going to go right on to icebergs then, which, okay, here's what you need to know. The verb for what happens when you take a floating chunk of ice and break it off to form an iceberg is called calve. So we say that icebergs are formed from calving. That can be either from mountain glaciers that have come down to the sea, Or I've just given you several examples of where ice sheet glaciers come down to the sea, and then pieces can break off to form icebergs. Once they're floating, they drift under the influence of wind and ocean currents. And don't forget to indicate that the Coriolis force can also play a big role in this too. For example, if the wind pushes on an iceberg in that direction, it'll move off at right angles. So that's because of the Coriolis force. They float with about 90% of their volume underwater. We'll work out the math for that in just a moment. That means there's a lot of ice underneath that you don't see, and if you're in a shallow part of the ocean, they can hit the bottom and get stuck. So very often you'll find icebergs that are not moving, even though the wind is pushing on them and the current is pushing on them, but they're just stuck in place. That would have to be because their bottom is touching, so they get stuck there. They tend to melt the fastest right around their waterline, right where the waves splash up against them. You tend to get this rapid melting right around the waterline. What that'll do is change the shape of these icebergs by carving away these grooves around the waterline, and at some point their shape changes so much that their current orientation is no longer stable. And then without warning, these things will suddenly begin to tip, and they'll roll to a new orientation and then stay that way for several weeks while melting continues around their new waterline. And that's rather remarkable if you get a chance to visit these latitudes, and if you see a broad field of icebergs, and if you're patient and wait a few minutes, because there's so many of them, you'll probably see one or two of them do that roll. And that's the reason why you don't want to be close to them, because when they roll, they'll put off a wave and they would swamp you if you're in a small boat. That'll happen suddenly without any warning. So I want to show this little calving movie. I found it on the web, and I want to be sure the sound is here. Let's see if I can get this to work here.
Oh, look at it go. Oh my gosh. Jimmy, you gotta get a picture of that. It's so tough. Wow. Woo! Look at all that. Captain is glad we're not next to that. Holy cow. I'm glad we're not next to that. Oh my gosh. Oh, look at the size. We're breaking the rubber up against the tidal wave. Everybody get off the deck. Oh.
I don't know what happened after that. So that's the calving process. So that ice has come out, and then eventually it has to break off pieces, and it happens kind of in a dramatic fashion, as you saw there. So from that, a bit of fun to the mathematics of the situation. So remember Archimedes' law. We've talked about it before in this course. It basically says that the buoyancy force pushing up on a submerged obstacle is submerged object is equal to the weight of the fluid displaced. So when you have an object like this, like an iceberg, floating in a stable configuration, there's going to be a balance of its own weight with the buoyancy force pushing it up. So I've left the acceleration of gravity off of both terms, but that'd be the same in both cases. So the weight would be the total volume of the iceberg times the density of ice, that product will give you the mass in kilograms of the total iceberg. And then that's going to be balanced by a buoyancy force pushing up, which is the volume submerged, it's only this part, multiplied by the density of the fluid displaced. Well, it's displacing seawater, so we use the density of seawater. So that's the statement of equilibrium for this floating object. If I simply divide through, I can get this expression. The ratio of the submerged part of the iceberg to the total is simply going to be dividing through the ratio of the two densities, rho ice over rho of seawater. And we've already used these values before. The density of ice is about 917 kilograms per cubic meter. Seawater with a salt is about 1,025. Divide that out, you get 0.9. So the point is the ratio of this part to the total is about 0.9 or 90%. So that is a solid derivation of why it is that most of the iceberg is below sea level there. Any questions on that? Okay, now a very interesting place on the west coast of Greenland is Jakobshavn. So here's the ice sheet, Greenland ice sheet out to the east. There's Baffin Bay to the west, and the glacier comes down here. But here's indicated where that calving front was in 1851, 1875, and back to 2003. So it's been retreating rather dramatically. But I want to make something clear to you that even when this retreats all the way back to here, this is where the calving is now taking place. Still, this channel is choked with ice. It's not open water. It's got lots of icebergs sitting in it, some of them making their way out, some of them grounded and kind of stuck there. But the calving front is back there. So again, the question is this a significant change? If the channel, if the fjord is still choked with ice, does it make any difference whether the calving is here or the calving is? I would think it would make a difference because, again, if you're calving back here, that's going to allow a faster flow down from the ice sheet. You're going to be moving more ice from the Greenland ice sheet if the calving is back here than if it has to go all the way up here before it can calve off. I was there last year and took some pictures. There's nothing for scale here, but that's about 40 meters high. And then when you think what lies below that, oh, and I'm looking across the channel. Through the little gap there, you can see the land on the other side of that fjord. But those are pretty impressive glaciers, just the part, icebergs, just the part that are above water. Here's a small ship for scale. You can get some idea. Has anybody seen something like this, traveled to high latitudes and seen something like this? Where were you? Antarctica. Oh, nice, yeah. They look a bit different in Antarctica, but the physics is the same. It depends on the shape of the ice, how much it's crumpled as it comes down before it breaks off, but basically you've got the same process happening in both hemispheres. The other reason I wanted to show you this particular location, Jakobshavn, is that there's good reason to think that it was a Jakobshavn iceberg that sunk the Titanic. And I want to show you the geometry of that. So here is Jakobshavn on the west coast of Greenland. And if an iceberg breaks off there, it will be carried first northward by the West Greenland current. Then at some point it'll get drawn into the Labrador current, come down past, if it's large enough, it'll be melting as it comes down through here, but if it's large enough, it'll persist and possibly get down into this area south of 50 north and maybe even south of 45 degrees north down in this area. And at that point now it becomes into the Great Circle route for ships between, say, New York and England. And that's what the Titanic was doing in April of 1912. It was making its way from, well, it started in Southampton, England, and it was making its way to New York, and that's where it hit the iceberg and sunk. So almost certainly it came from the west coast of Greenland, and because Jakobshavn is known to be the most prolific generator of icebergs, I guess it's a fair guess that it was one of those Jakobshavn icebergs that was the one that did the deed for the Titanic. Any questions on that? Okay, now we'll turn to mountain glaciers. And there again, a bit like the ice sheets, you have an accumulation zone and an ablation zone. So every year, a full 12 months that goes by, you've added a bit of ice here, and that cannot continue. You've got to balance that mass in some way, and that is eventually balanced by a flow, a liquid-like flow down the mountain slope by the glacier itself. Some of it is accomplished by distorting the ice, and some of it is accomplished by just sliding the ice along the bottom. But in any case, it is moving under the influence of gravity. And then, in some cases, it makes it all the way down to the ocean surface. Question, yeah?
Can you explain what you mean by distorting the ice?
So if you do a viscous experiment, if you, let me get the lights on for a second. If you tilt your pancake and pour that syrup on it, you'll find that the syrup is not slipping along the bottom. It actually has a shear within it. Glaciers do some of this, but they also slip a little bit along their base. So it'd be more accurate to draw it like this. There's some internal deformation, but there's also some slip right at the bottom. So it's a combination of the two that allows it to slide down the slope like that. Thanks for that. So, okay, so in this case, for these two glaciers in Alaska, they've actually made it all the way down to sea level. This one easily, this one just barely. But in any glacier that makes it down to sea level is called a tidewater glacier. It makes it down, and then partly because of the tides, but it would happen anyway, you'll get calving and you produce icebergs. So a tidewater glacier will produce icebergs that will then float out over the sea. You're likely to have these in high latitudes. Remember, you can have mountain glaciers in low latitudes too. Mount Kilimanjaro in Africa, almost exactly on the equator, has a glacier at the top, but it certainly doesn't come down very far, and it certainly does not reach any ocean where you would produce icebergs. But these tidewater glaciers do produce icebergs. Here's an example in Alaska of one that does not, Stevens Glacier. So you can see glaciers from various parts of the mountain chain combining and merging. Here's the last merger right here. But then there's the terminus of the glacier. There is some meltwater, and the river will carry that water away to the sea. The water will get to the sea, but not the ice itself. So this is happening more and more as the climate warms and glaciers retreat. Their terminus moves further up, but eventually, that water, of course, always returns to the sea. Very often you can see the seam where two glaciers come together. You have a little bit of rock rubble, and in some glaciers you can see way down at their snout, you can see 5 or 6 of these little black lines, and if you trace them back, each one of them originates at a point like this. So you can actually keep track of all the tributaries by the little line of rock rubble that gets permanently put into the glacier. Questions there? So again, the speed of these things are quite slow. They might be only a few centimeters per day or a few centimeters per week in some cases. But what they can do is drive a stake here, go up on the bedrock, triangulate, get the location, and then come back a week or two later and see how much that stake has moved. And that will at least give you the speed of the ice at the top of the glacier. It won't give you everything you need to know about the depth all the way through, the speed down through the glacier. Here's a couple of glaciers from Norway. The word, Bray simply means ice or glacier, and so all the glaciers in Norway end with the suffix Braen, but there's the one in Berksdal and there's the one in Yen, and of course Dal, this means valley in Norwegian, so Jensdal's Glacier and Björk's Valley Glacier, they're all named like that, but these are not tidewater glaciers. This is not the sea, this is a little lake at the bottom of the glacier, a freshwater lake. And it has that milky appearance to it because underneath the glacier, where there's a grinding process going on, you're developing a kind of powder from the grinding of rock, and that ends up in the water. And then if you see that river, even miles away, it'll have that characteristic milky appearance. And you can say that one came from a glacier. That river water came from a glacier because it has that so-called glacial milk in it that's characteristic of water that flows out from a mountain glacier like that. Questions there? Here's another one. You see the terminus of that and the water rushing out from underneath in that stream. We are, let's see, yeah, I guess we'll quit here and just finish up. There's just a little bit left on ice, but I want to do a good job on that, so we'll wait until Monday and finish that up.